Okay, so this is a set of notes on the power series. Okay, so what is a power series? A power series is basically you have some sequence of CNs. Okay, so you have C1 or C0, C1, C2, C3, and you have some other real number, right? And then we're going to build a series. Now you're going to want to note this, that this is n equals 0. 0, not 1. 0, right? N equals 0 to infinity of C sub n times x to x minus a to the n. Okay, so this is like the general form of a power series. This is what we call a power series centered at a. Okay, so x is truly a variable here. So x can take on various values. N is the thing being iterated. So don't confuse the x's with the n's in this thing. X can take on various values. N is something that can be iterated. What makes power series interesting is that they are essentially a polynomial with right, with an infinite number of terms, right? So this is going to give you like x minus a to the 0, x minus a to the 1. So you're going to get a constant term, an x squared term, an x cubed term. It's going to look like a polynomial. All right, so we're going to give as an example like the baseline power series, and we're going to kind of play around with this a little bit today, and we'll show some of the reasons why we care. Okay, the quickest and easiest power series to create is n equals 0 to infinity of x to the n. Okay, so this guy, like, if you think about this, C sub n is 1 for all n, and a equals 0. So this thing is centered at 0, and all the coefficients are 1. If you expand this series, you get 1 plus an x plus x squared out to x to the n, and it just keeps going, right? So this is like basic polynomial. All right, so let's play around with this. So let's actually subject this thing to the ratio test. So if I take the limit as n approaches infinity of the absolute value of x to the n plus 1 over x to the n, I get the absolute value of x. Okay, so, well, I get the limit as n approaches infinity of the absolute value of x. But note, there's no n in here anymore. So if n goes to infinity, it's just going to whatever this is. Now, if the absolute value of x is less than 1, this clearly converges. Okay? If the absolute value of x is greater than 1, this thing clearly diverges. Okay, so this thing has convergence when the absolute value of x is less than 1, when it's greater than 1. Well, what about when it equals 1? Well, there's two possibilities. If the absolute value of x is equal to 1, this implies that either x is 1 or x is negative 1. So if we build the series and we let x equal 1, that's 1 to the n equals 0 to infinity. This is just like the series from n equals 0 to infinity of 1. Well, the limit as n approaches infinity of 1 is equal to 1, which is not 0. So by the divergence test, this thing diverges. So at 1, we diverge. So what about negative 1? Well, if we take the series as n equals 0 to infinity of negative 1 to the n, right? Well, this thing is going to take, well, if I take the limit as n approaches infinity of negative 1 to the n, that goes oscillating, right? So that's going to go -1, 1, -1, -1. So that limit does not exist, which means that it does not equal to 0. So again, by the divergence test, this diverges. So this thing only converges when the absolute value of x is less than 1. Now, this should not really be shocking to us. So let's kind of recap a little bit of what we're saying, and then we'll show why that's not shocking. Okay, so important facts that we just gleaned, that if I have the series from n equals 0 to infinity of x sub n, this thing has a center at 0. So we'll get into what does that mean later on, but it's a pretty significant fact that it has a center at 0. Number 2, it has a radius of convergence of r equals 1. Okay, so what does this mean? This means that if I go 1 unit from the center, so that means from -1 to 1, it still converges. So I get 1 unit from either side of the center and I still have convergence. Number 3, the interval of convergence is strictly -1 is less than x is less than 1. I don't get the equals here. We've proven that the boundaries here are not convergent. We showed that a minute ago. Okay, so these are 3 quick facts that I get about this series. But here's why we should not be surprised by any of this. Because if you look carefully at this series, n equals 0 to infinity of x to the n, this is the same as the series equals n1 to infinity of x to the n minus 1. Right? Because if I move the marker by 1 here, I have to move it by 1 here. Means this thing is geometric. If it's geometric, it converges when r, which in this case is the x, the absolute value of x, whoops, is less than 1. Okay, and it diverges elsewhere. So this is not unexpected. But what does this converge to? Well, this means that this thing converges to the n minus 1 is going to equal 1 over 1 minus x, according to, because r in this case is x, and this is a would be 1, right? 1, r is x, so this is 1 over 1 minus x. Now, this is kind of a big deal. Okay, so when this series converges, it converges to this. So let's not miss the detail here. Okay, so what we have just said is that 1 over 1 minus x is equal to the sum from n equals 0 to infinity of x to the n when -1 is less than x is less than 1. We've made a connection between a function, f of x, and a series. And we can pass back and forth between them on a particular domain. Now, what's nice about this is this function is actually rather difficult to work with sometimes, but this series is in the form of a polynomial. Okay, and like taking an integral or taking a derivative of a polynomial is very, very simple. And what we actually have names for these things. So this is ultimately, we're going to look at some of the broader implications of this when we do Taylor and Maclaurin series. In fact, the series that we're looking at here is in fact a Maclaurin series, but we'll get into that a little bit later into the next unit. But this is our first basic power series that we're going to work with. So there's a lot going on here. We're going to kind of start picking at this here. We're going to get into intervals of convergence in the next lesson. And then we're going to stop for a little bit so we can take an assessment. And then we're going to take a big deep dive into particular types of power series that are called Taylor and Maclaurin series that are all build the coefficients in a very particular way. So this is like we're at the edge of Taylor and Maclaurin series here. All right, so I'm getting excited about this because there's lots of good stuff happening here. But I'm going to stop there, let you be able to soak this all in, and we'll do some work with this in our next class.